Hello all, in this presentation we will be discussing our research on persistence in Linux-based malware. First, we will cover some of the background, briefly covering the Internet of Things and IoT malware in general. Next, we will define persistence, why it's important, and the associated challenges for achieving it on IoT devices. We will then discuss our approach when researching potential methods of gaining persistence, followed by our tests on various IoT devices. Finally, we will provide some countermeasures and summarize our findings. The Internet of Things is a rapidly growing collection of smart devices capable of communicating over the Internet. Some examples of IoT devices include surveillance cameras, virtual assistants, DVRs, and smart TVs. While it can be argued that any device that can connect to the Internet could be considered an IoT device, in the context of this paper, we consider an IoT device an Internet-connected device with constrained capabilities designed to perform a predefined function. Many different families of IoT malware have already been produced, such as Mirai, IoTroop, and Bashlight. However, most IoT malware does not make persistent changes. Instead, previous IoT-based malware typically relies on worm-like behavior to retain control over a large number of devices as part of a botnet. Instead of attempting to gain persistence, each infected device will scan the Internet for other potentially vulnerable devices to propagate to. One piece of advice often given to victims is to simply reset the device if it is infected with malware. If the user does restart the device, either deliberately or intentionally, it will remove the infection, as none of the changes the malware makes are permanent. However, it will not remove the underlying issue, and the device can easily be reinfected, sometimes within minutes. As most IoT malware does not attempt to make persistent changes, attackers instead need to compete with one another to find new victims and retain control of infected devices. Some malware even add features that prevent or remove other attackers' infections, such as shutting down vulnerable services to prevent exploitation, or killing competing malware processes. Persistence allows malware to continue operation even after a device has been restarted. For desktop operating systems, malware normally achieves this by saving itself to the file system, then modifying the system configuration so that it will be run when the device boots. For example, the .bashrc or crontab files on Linux can determine which applications are set to run on boot. There are several benefits for the attacker if they are able to make persistent changes. Firstly, it will be easier to retain control of the device, as they will be able to make permanent changes to the behavior, potentially even patching vulnerabilities to prevent other attackers from gaining access. This will mean attackers will no longer need to protect their devices from other infections or prevent their own malware from being removed. There will also be more opportunities to use more creative payloads on the device. Many IoT botnets focus on the ability to perform distributed denial of service attacks, but if the attacker can retain control of the device, it could be used for other purposes, such as for long-term network backdoors, malware distribution, or even ransomware. The attacker could also implement safeguards to prevent remediation attempts by the victim, such as updates or factory resets. While they are significantly rarer, there have been instances of persistent malware. Two examples of this are Tori and VPN filter. Both modify files native to the Linux operating system which allow the malware to automatically run after booting. VPN filter is a piece of malware that mainly targets routers and storage devices. When it infects a device, it aims to modify the crontab file to run the malware every 5 minutes. Tori, on the other hand, has a more brute force approach. It attempts to use 6 methods to gain persistence on the infected device by modifying various startup scripts, such as bashrc, Initrd, and crontab. However, these methods rely on the startup scripts being writable, which, depending on the design of the device, may not be the case. So why can persistence be difficult to obtain? There are a couple of reasons, one of which being that IoT devices utilize cheap and effective flash memory to store their data. Data stored on the device is often separated into different partitions based on their content, such as kernel images or configuration files. In Linux, these partitions are typically defined and managed via the MTD subsystem. How these partitions are configured is down to the developer of the device. Some data stored on an IoT device is unlikely to be modified after development, such as the bootloader. As such, it may benefit the developer to mark some data as read-only, as to prevent accidental modification during system operation. If these read-only flags are set, it will not be possible to modify these partitions from the Linux operating system until the flags are unset by the kernel. Additionally, these flash chips often have limited space. Ideally, file systems should be as small as possible, as this will reduce the hardware costs. To further complicate things, one of the downsides of flash memory is that it can wear out. Data can only be wiped and rewritten a certain number of times before the flash chip will start to fail. To reduce the amount of space and writes needed, many devices make use of compressed file systems, such as CramFS and SquashFS, for files which are unlikely to change often. One downside of this is that when data is compressed, it is not easy to modify. To change a file, a user would need to extract all of the original files, modify the file in question, and then recompress the whole file system. For files that do not need to persist through reboots, or need to be modified often, devices can employ a second temporary file system, which is stored entirely in RAM. This allows the bulk of the data, which is unlikely to be changed, to be stored in the read-only compressed file system, while files that need to be used and modified during the running of the device, such as the status of the application or the operating system, can be stored in the temporary file system. IoT devices can vary a lot more heavily than traditional desktop systems. Different exploits are required for differing software and architectures. File systems influence how modifications can be made, while hardware can change how an attacker is able to communicate with the storage devices. This has the unintended effect of making it more difficult for malware authors to create a universal method for gaining persistence. Due to the level of variance shown between devices, we do not believe creating a single universal solution to gaining persistence would be a viable strategy. We decided to test whether it would be feasible for an attacker to gain persistence on a variety of IoT devices. For a realistic test scenario, we set a couple of restrictions for ourselves as attackers. For a persistence method to be considered valid, first, the method must not require the attacker to have physical access to the device. They must be able to achieve persistence remotely, preferably over the internet. Second, the attacker must be able to force the device to run arbitrary code when the device is rebooted. Cosmetic or configuration changes are not valid. As mentioned earlier, due to the variance of IoT devices, we did not believe that a single universal method was the solution. Instead, we aim to use a collection of methods to try and gain persistence. As a result of our research, we produced a list of 6 methods that can be used by potential attackers to gain persistence on a variety of IoT devices. We will now go over how each of these methods work, their requirements, and their potential drawbacks. Some IoT devices make use of writable journal-type file systems. If the file system flash partition does not have the read-only flag set by MTD, and the device implements one of these writable file systems, the attacker will be able to make modifications from the shell, just like any traditional desktop PC. In an ideal situation, they will be able to save their malware onto the device. If the writable file system contains a script that is run when the device is booted, the attacker can modify it to call the malware when the device is started. This was a technique that was used by Tori and VPN Filter. However, while it is very simple to implement, this method will only work on devices that implement a writable file system, which is quite restrictive. Many devices, as described previously, may instead use a compressed write-only file system to save space and write cycles. Unfortunately, this makes it difficult to modify just one file, as it will impact how the rest of the file system is compressed. Instead, the attacker can attempt to replace the entire file system. First, the attacker must copy the compressed file system to an external computer, as the device being attacked is unlikely to contain the tools necessary to recreate the file system. The attacker can then use tools on the external device to extract the compressed file system. At this point, they should write the malware to a useful directory and modify one of the startup scripts to execute it when the device boots. Once the attacker is satisfied with their modifications, they can recompress the file system to the same format as the original. For SquashFS file systems, for example, the attacker can use the MakeSquashFS utility. Once the file system has been compressed, the attacker can force the victim's device to download it to temporary memory. The attacker can then write the new file system to the required flash partition via /proc mtd block with the correct index. Now the infected file system has been written to flash, when the device is next booted, the new file system will be loaded, running the modified startup script and starting the malware. As part of the booting process, the Linux kernel can be set to use an Initrd or Initramfs file system, which is normally appended to the end of the kernel. If the attacker is able to modify the kernel partition of the device, they may be able to modify this appended file system. First, the attacker must copy the kernel partition to an external device. The attacker must then analyze it to determine if an Initrd or Initramfs file system is being used. Once the correct offset of the file system has been identified, the attacker must separate it from the kernel. Typically, the file system will be contained within a CPIO archive and may have additional layers of compression. The attacker may need to perform multiple extraction steps to access the files within, at which point they can make the necessary modifications. Once they have completed the changes, the extraction steps must then be reversed to recreate the expected format. The new file system can then be reappended to the original kernel. Finally, if the kernel has any headers used by the bootloader, such as with U-boot images, the attacker may need to recreate them, as they often include checksums to protect against corruption, which will not match the new kernel data. This is more of a supplementary method, as it cannot gain persistence by itself, but it can assist when using other methods. As mentioned previously, the developer can use the MTD subsystem to mark certain partitions as read-only on boot. This may prevent some of the listed methods from being used. It is not possible to modify the MTD read-only flag from user space, as this is managed by the kernel. However, if the attacker can insert a loadable kernel module for the device, it will have the necessary privileges to unset any set read-only flags. Creating a loadable kernel module typically requires the kernel source code or headers. While it is possible to create it without them, having the source code will drastically increase the likelihood of the module being compatible with the kernel. One possible method the attacker may use is to check if the source code for the kernel is released under the GPL license, which can then be used to compile the module. After compilation, the attacker can upload and insert the module. When the read-only flags have been unset, they can proceed with attempting one of the other methods. In some cases, a device may implement a vulnerable update function. If an attacker gains access to such a function and updates are not sufficiently validated, the attacker may be able to forge a custom update with the malware included. They can then provide the fake update to the update process, which will replace the original firmware. This is, however, quite niche, as devices often require you to authenticate before being able to access the update function. The update's file format and firmware headers can vary heavily depending on the device being exploited. The attacker would likely have to create a custom process for each device that they aim to target using this method, so this method might be quite time-consuming. Researchers have produced an attack named U-Bootkit, a bootkit targeting the U-Boot bootloader. If the attacker can modify the bootloader partition, U-Bootkit would allow attackers to corrupt the boot process of the device. First, the attacker modifies the bootloader to include arbitrary code execution as part of the boot process. When the device next boots, the modifications made will temporarily take control and hot patch the kernel loaded in memory. Execution is then passed from U-Boot to the kernel. The modified code will then append lines to the RCS script file, which is run when the device is booted. This script, when run, will force the device to download and run malware from an external source. This is a very complex technique that requires hot patching assembly in both the bootloader and the kernel, as the code and the offsets will differ for each firmware version on each device model. Determining the required modifications would be quite time-consuming. While we now have a collection of potential methods that could be used to gain persistence on a device, how would the attacker determine the correct method to use? The attacker could attempt to brute force each method one by one, but this is likely to break the device if not performed correctly. Instead, there are a number of files available on the device that the attacker can use to gather information. For example, the /procmtd file lists the partition names and sizes used on the device, while the procmounts file identifies file system types and where they are mounted. These may indicate to an attacker which methods would be viable according to their requirements and ease of use. In order to test the various persistence methods, we attempted to implement them on 4 IoT devices of varying brand and purpose, including a router, camera, presenter, and voice over IP phone. We chose these devices as they had publicly available exploits that would allow an attacker to gain shell access remotely. Some of these devices have also previously been targeted by existing IoT malware. The write-ups for the other devices are available in the paper. In order to gain remote shell access and begin reconnaissance, we used a command injection vulnerability present in the router's web server. First, we read the procmounts file and found that the router used both a JFFS2 and squashfs file system. Initially, we targeted the JFFS2 file system, as it is writable by default. However, it only contained configuration files, so while we were able to make persistent changes and save them out to the device, we would have no way of setting it to run the next time the device booted. Instead, we targeted the squashfs file system, which was mounted at the root directory. We read the procmtd file and identified a partition named rootfs, and after extracting the partition to an external device, we found it was using SquashFS version 4.0 with XZ compression. After extracting the file system, we added a test file into the /bin directory. We then recompressed the file system using the mk-squashfs utility, setting the required arguments to use the expected XZ compression format. Finally, we used our shell access to copy the infected file system to the temporary memory, before writing it to the appropriate mtd partition via /proc mtd block 15. When we rebooted the device, we found that the test file was readable, indicating that we could make persistent edits to any file under the root directory. During our exploitation of the device, we also noticed that some of the mtd partitions, such as the bootloader, had been marked as read-only, as we were not able to edit them. While we had already achieved persistence on the router, we decided to take this opportunity to also test the loadable kernel module method. Kernel modules for this purpose have already been developed. In this case, we used a project named mtd-rw. We searched on the Netgear website and found a support webpage that hosted all the open source code used under the GPL license, where we found the source code for our model and firmware version. After setting up a compatible development environment, we successfully compiled a loadable kernel module using the kernel headers. We uploaded the module to the router and used the insmod command to insert the module into the kernel. We were then able to modify the read-only flags from user space, which would improve the chances of gaining persistence. There was significant variation in the structure of the devices that we exploited, with different types of storage implementations requiring different methods to be effective. However, we were able to gain persistence on every device using these methods. While we performed these attacks manually for this paper, we found that the device reconnaissance step was very time-consuming. For this to be viable for large-scale attacks, automation of this process would be essential. While hard-coding the best method for each device would be a possibility, this would require the attacker to manually identify the best method for each device. We were also able to take what we learned when manually exploiting the devices and visualize our process for identifying and implementing the best method for gaining persistence. The full version of this flowchart is available in our paper. We propose several countermeasures that could be used to mitigate the risk posed by these persistence methods. While it should be noted that there is no perfect countermeasure, each method that is used will frustrate attackers' attempts and make your device a less appealing target. One of the best steps we can take to prevent this type of attack is to patch vulnerabilities and prevent device exploitation. This is one of the more obvious countermeasures, but users should update their devices regularly to prevent attackers from being able to access the device or install malware. Signatures can be used to verify that data stored on the device has not been modified by an unauthorized party. Unless the attacker has access to the required private keys, they will not be able to make signatures of their own. U-boot, for example, has a trusted boot feature to verify images before it begins the boot process. Each stage will require a signature so that the device can create a chain of trust. It should be noted that, if possible, the first stage should be immutable such that the attacker cannot corrupt the boot process. All of the techniques that have been discussed so far required the attacker to modify data stored on the device. The device could run potentially vulnerable services at lower privileges and only allow certain privileged accounts to interact with flash memory. If the attacker was able to exploit one of these services, they would not be able to make any persistent changes with the privileges they obtain. In order to attempt using one of the persistence methods, they would first need to find another vulnerability on the device and escalate their privileges so that they can interact with flash. Hades IoT is a system designed for use on IoT devices that allows designers to profile and whitelist processes. Developers can use a profiling stage to automatically create whitelists of expected processes for their device. When a new process is spawned, Hades can compare it against a list of benign executables, preventing unknown processes from being created. This can frustrate attackers attempting to gain persistence and prevent uploaded malware from running. Often, devices will include a method of being able to reset the device to factory settings. Unfortunately, how this is implemented changes from device to device. For example, if only the configuration partition is reset, the malware is unlikely to be effectively removed. The more active sectors that are wiped, the more effective the factory reset will be in removing persistent malware. In summary, we investigated the increasing threat of persistent IoT malware. We outlined the potential challenges that prevent current malware from easily gaining persistence. We detailed methods that attackers could potentially employ in the future to gain persistence. We tested these methods on 4 vulnerable devices, gaining persistence on all of them. And finally, we proposed several countermeasures that could be employed to prevent this type of attack from succeeding. Thank you for listening.